Diffusion is the net movement of molecules or atoms from a region of high concentration to a region of low concentration. This is also referred to as the movement of a substance down a concentration gradient. A gradient is the change in the value of a quantity with the change in another variable. For example, a change in concentration over a distance is called a concentration gradient. A change in pressure over a distance is called a pressure gradient, and a change in temperature over a distance is called a temperature gradient. The word diffusion is derived from the Latin word diffundere, which means to spread out. A distinguishing feature of diffusion is that it results in mixing or mass transport, without requiring bulk motion. Thus, diffusion should not be confused with convection, or advection, which are other transport phenomena that utilize bulk motion to move particles from one place to another. Diffusion versus bulk flow. An example of a situation in which bulk flow and diffusion can be differentiated is the mechanism by which oxygen enters the body during external respiration. The lungs are located in the thoracic cavity, which is expanded as the first step in external respiration. This expansion leads to an increase in volume of the alveoli in the lungs, which causes a decrease in pressure in the alveoli. This creates a pressure gradient between the air outside the body and the alveoli. The air moves down the pressure gradient through the airways of the lungs and into the alveoli until the pressure of the air and that in the alveoli are equal. The air arriving in the alveoli has a higher concentration of oxygen than the stale air in the alveoli. The increase in oxygen concentration creates a concentration gradient for oxygen between the air in the alveoli and the blood in the capillaries that surround the alveoli. Oxygen then moves by diffusion down the concentration gradient into the blood. The other consequence of the air arriving in alveoli is that the concentration of carbon dioxide in the alveoli decreases. This creates a concentration gradient for carbon dioxide to diffuse from the blood into the alveoli. The blood is then transported around the body by the pumping action of the heart. As the left ventricle of the heart contracts, the volume decreases, which causes the pressure in the ventricle to increase. This creates a pressure gradient between the heart and the capillaries, and blood moves through blood vessels by bulk flow. As the thoracic cavity contracts during expiration, the volume of the alveoli decreases and creates a pressure gradient between the alveoli and the air outside the body, and air moves by bulk flow down the pressure gradient. Diffusion in the context of different disciplines. The concept of diffusion is widely used in physics, chemistry, biology, sociology, economics, and finance. However, in each case, the object that is undergoing diffusion is spreading out from a point or location at which there is a higher concentration of that object. There are two ways to introduce the notion of diffusion. Either a phenomenological approach starting with fixed laws of diffusion and the mathematical consequences, or a physical and atomistic one, by considering the random walk of the diffusing particles. In the phenomenological approach, diffusion is the movement of a substance from a region of high concentration to a region of low concentration without bulk motion. According to fixed laws, the diffusion flux is proportional to the negative gradient of concentrations. It goes from regions of higher concentration to regions of lower concentration. Sometime later, various generalizations of fixed laws were developed in the frame of thermodynamics and non-equilibrium thermodynamics. From the atomistic point of view, diffusion is considered as a result of the random walk of the diffusing particles. In molecular diffusion, the moving molecules are self-propelled by thermal energy. Random walk of small particles in suspension in a fluid was discovered in 1827 by Robert Brown. The theory of the Brownian motion and the atomistic backgrounds of diffusion were developed by Albert Einstein. The concept of diffusion is typically applied to any subject matter involving random walks in ensembles of individuals. In biology, the terms net movement or net diffusion are often used when considering the movement of ions or molecules by diffusion. For example, oxygen can diffuse through cell membranes, and if there is a higher concentration of oxygen outside the cell than inside, oxygen molecules will diffuse into the cell. However, because the movement of molecules is random, occasionally oxygen molecules will move out of the cell. Because there are more oxygen molecules outside the cell, the probability that oxygen molecules will enter the cell is higher than the probability that oxygen molecules will leave the cell. Therefore, the net movement of oxygen molecules will be into the cell. In other words, there will be a net movement of oxygen molecules down the concentration gradient. History of diffusion in physics. In the scope of time, diffusion in solids was used long before the theory of diffusion was created. For example, Pliny the Elder had previously described the cementation process, which produces steel from the element iron through carbon diffusion. Another example is well known for many centuries, the diffusion of colors of stained glass or earthenware and Chinese ceramics. In modern science, the first systematic experimental study of diffusion was performed by Thomas Graham. He studied diffusion in gases, and the main phenomenon was described by him in 1831 to 1833. Gases of different nature, when brought into contact, do not arrange themselves according to their density, the heaviest undermost, and the lighter uppermost, but they spontaneously diffuse, mutually and equally, through each other, and so remain in the intimate state of mixture for any length of time. The measurements of Graham contributed to James Clerk Maxwell deriving, in 1867, the coefficient of diffusion for CO2 in air. The error rate is less than 5%. In 1855, Adolf Fick, the 26-year-old anatomy demonstrator from Zurich, proposed his law of diffusion. He used Graham's research, stating his goal as the development of a fundamental law for the operation of diffusion in a single element of space. He asserted a deep analogy between diffusion and conduction of heat or electricity, creating a formalism that is similar to Fourier's law for heat conduction and Ohm's law for electric current. Robert Boyle demonstrated diffusion in solids in the 17th century by penetration of zinc into a copper coin. Nevertheless, diffusion in solids was not systematically studied until the second part of the 19th century. William Chandler Roberts Austin, the well-known British metallurgist, and former assistant of Thomas Graham, studied systematically solid-state diffusion on the example of gold in lead in 1896. My long connection with Graham's research has made it almost a duty to attempt to extend his work on liquid diffusion to metals. In 1858, Rudolf Clauses introduced the concept of the mean free path. In the same year, James Clerk Maxwell developed the first atomistic theory of transport processes in gases. The modern atomistic theory of diffusion and Brownian motion was developed by Albert Einstein, Marian Smoluchowski and Jean-Baptiste Perard. Ludwig Boltzmann, in the development of the atomistic backgrounds of the macroscopic transport processes, introduced the Boltzmann equation, which has served mathematics and physics with a source of transport process ideas and concerns for more than 140 years. In 1921, George de Hevesy measured self-diffusion using radioisotopes. He studied self-diffusion of radioactive isotopes of lead in liquid and solid lead. Yakov Frenkel proposed, and elaborated in 1926, the idea of diffusion in crystals through local defects. He concluded, the diffusion process in condensed matter is an ensemble of elementary jumps and quasi-chemical interactions of particles and defects. He introduced several mechanisms of diffusion and found rate constants from experimental data. Sometime later, Carl Wagner and Walter H. Schottky developed Frenkel's ideas about mechanisms of diffusion further. Presently, it is universally recognized that atomic defects are necessary to mediate diffusion in crystals. Henry Eyring, with co-authors, applied his theory of absolute reaction rates to Frenkel's quasi-chemical model of diffusion. The analogy between reaction kinetics and diffusion leads to various nonlinear versions of Fick's law. Basic models of diffusion. Diffusion flux. Each model of diffusion expresses the diffusion flux through concentrations, densities and their derivatives. Flux is a vector. The transfer of a physical quantity through a small area with normal per time is whereas the inner product and is the little o notation. If we use the notation of vector area, then the dimension of the diffusion flux is flux equals quantity. The diffusing physical quantity may be the number of particles, mass, energy, electric charge, or any other scalar extensive quantity. For its density, the diffusion equation has the form where is intensity of any local source of this quantity. For the diffusion equation, the no-flux boundary conditions can be formulated as on the boundary, where is the normal to the boundary at point. Fick's law and equations. Fick's first law. The diffusion flux is proportional to the negative of the concentration gradient. The corresponding diffusion equation is where is the Laplace operator. Onsager's equations for multi-component diffusion and thermodiffusion. Fick's law describes diffusion of an admixture in a medium. The concentration of this admixture should be small and the gradient of this concentration should be also small. The driving force of diffusion in Fick's law is the anti-gradient of concentration. In 1931, Lars Onsager included the multi-component transport processes in the general context of linear non-equilibrium thermodynamics. For multi-component transport, where is the flux of the ith physical quantity and is the jth thermodynamic force. The thermodynamic forces for the transport processes were introduced by Onsager as the space gradients of the derivatives of the entropy density S, where are the thermodynamic coordinates. For the heat and mass transfer, one can take in is the concentration of the ith component. The corresponding driving forces are the space vectors because where T is the absolute temperature and is the chemical potential of the ith component. It should be stressed that the separate diffusion equations describe the mixing or mass transport without bulk motion. Therefore, the terms with variation of the total pressure are neglected. It is possible for diffusion of small admixtures and for small gradients. For the linear Onsager equations, we must take the thermodynamic forces in the linear approximation near equilibrium, where the derivatives of S are calculated at equilibrium n*. The matrix of the kinetic coefficients should be symmetric and positive definite. The transport equations are here. All the indexes I, j, k equals 0, 1, 2. Are related to the internal energy and various components. The expression in the square brackets is the matrix of the diffusion, thermodiffusion and thermal conductivity coefficients. Under isothermal conditions T equals const. The relevant thermodynamic potential is the free energy. The thermodynamic driving forces for the isothermal diffusion are antigradients of chemical potentials, and the matrix of diffusion coefficients is. There is intrinsic arbitrariness in the definition of the thermodynamic forces and kinetic coefficients because they are not measurable separately, and only their combinations can be measured. For example, in the original work of Onsager, the thermodynamic forces include additional multiplier T, whereas in the course of theoretical physics this multiplier is omitted, but the sign of the thermodynamic forces is opposite. All these changes are supplemented by the corresponding changes in the coefficients and do not affect the measurable quantities. Non-diagonal diffusion must be nonlinear. The formalism of linear irreversible thermodynamics generates the systems of linear diffusion equations in the form if the matrix of diffusion coefficients is diagonal, then this system of equations is just a collection of decoupled Fick's equations for various components. Assume that diffusion is non-diagonal, for example, and consider the state with, at this state. If at some points then becomes negative at these points in a short time. Therefore, linear non-diagonal diffusion does not preserve positivity of concentrations. Non-diagonal equations of multi-component diffusion must be nonlinear. Einstein's mobility and JrPol formula. The Einstein relation connects the diffusion coefficient and the mobility, where d is the diffusion constant, mu is the mobility, kb is Boltzmann's constant, T is the absolute temperature. Below, to combine in the same formula the chemical potential mu and the mobility, we use for mobility the notation. The mobility-based approach was further applied by JrPol. In 1935, he studied the diffusion of ions through a membrane. He formulated the essence of his approach in the formula: the flux is equal to mobility times concentration times force per gram ion. This is the so-called JrPol formula. The force under isothermal conditions consists of two parts: diffusion force caused by concentration gradient, electrostatic force caused by electric potential gradient. Here R is the gas constant, T is the absolute temperature, N is the concentration. The equilibrium concentration is marked by a superscript EQ. Q is the charge and phi is the electric potential. The simple but crucial difference between the JrPol formula and the Onsager laws is the concentration factor in the JrPol expression for the flux. In the Einstein-JrPol approach, if for the finite force the concentration tends to zero, then the flux also tends to zero, whereas the Onsager equations violate this simple and physically obvious rule. The general formulation of the JrPol formula for non-perfect systems under isothermal conditions is where mu is the chemical potential. Mu0 is the standard value of the chemical potential. The expression is the so-called activity. It measures the effective concentration of a species in a non-ideal mixture. In this notation, the JrPol formula for the flux has a very simple form. The standard derivation of the activity includes a normalization factor and for small concentrations, whereas the standard concentration. Therefore, this formula for the flux describes the flux of the normalized dimensionless quantity. JrPol formula for multi-component diffusion. The JrPol formula with combination of Onsager's definition of the diffusion force gives where is the mobility of the ith component, is its activity, is the matrix of the coefficients, is the thermodynamic diffusion force for the isothermal perfect systems. Therefore, the Einstein-JrPol approach gives the following multi-component generalization of the Fick's law for multi-component diffusion, whereas the matrix of coefficients. The Chapman-Enskog formulas for diffusion in gases include exactly the same terms. Earlier, such terms were introduced in the Maxwell-Stephan diffusion equation. Jumps on the surface and in solids. Diffusion of reagents on the surface of a catalyst may play an important role in heterogeneous catalysis. The model of diffusion in the ideal monolayer is based on the jumps of the reagents on the nearest free places. This model was used for CO on PT oxidation under low gas pressure. The system includes several reagents on the surface. Their surface concentrations are: the surface is a lattice of the adsorption places. Each reagent molecule fills a place on the surface. Some of the places are free. The concentration of the free places is: the sum of all is constant. The density of adsorption places B. The jump model gives for the diffusion flux if the corresponding diffusion equation is due to the conservation law, and we have the system of M diffusion equations. For one component we get Fick's law and linear equations because, for two and more components, the equations are nonlinear. If all particles can exchange their positions with their closest neighbors, then a simple generalization gives where is a symmetric matrix of coefficients which characterize the intensities of jumps. The free places should be considered as special particles with concentration. Various versions of these jump models are also suitable for simple diffusion mechanisms in solids. Diffusion in porous media. For diffusion in porous media, the basic equations are, where d is the diffusion coefficient, n is the concentration, m greater than 0. For diffusion of gases in porous media, this equation is the formalization of Darcy's law. The velocity of a gas in the porous media is where K is the permeability of the medium, mu is the viscosity and P is the pressure. The flux J equals Nevada, and for Darcy's law gives the equation of diffusion in porous media with M equals gamma plus 1. For underground water infiltration, the Boussinesq approximation gives the same equation with M equals 2. For plasma with a high level of radiation, the Zeldovich-Riser equation gives M greater than 4 for the heat transfer.